What is up, young chemists? Mr. Rosen here. Today we're going to talk about Hess's law. This is usually in a unit on thermodynamics. Hess's law is useful to chemists because it allows them to solve for the heat of reaction indirectly. It allows them to solve for heat of reaction without actually having to do the reaction itself, but instead by using other known equations. All right, so Hess's law of heat summation, it's just called Hess's law for short, states that regardless of the multiple steps or stages in a reaction, the total enthalpy change for the reaction is the sum of the individual changes. Right? Stated another way, any heat of reaction is equal to the sum of the heats of reactions for any set of equations that in sum are equivalent to the overall reaction. This is really a kind of a bit of a mouthful. It seems like a lot of words and it seems a little bit confusing. But to try to put it in more straightforward terms, if you have multiple chemical equations, and you can add those equations together to get an equation of interest, you can add the heat of reaction values together to solve for the heat of reaction for the equation of interest. Even still, that was me attempting to explain it in easy words, but the easiest way, I think, to understand this is to just do practice problems. Okay, and Hess's law is it's convenient because it allows chemists to measure heat of reaction indirectly. All right? So let's start off with an example problem. We're going to start off with an easy example problem, and then we're going to touch on some big ideas related to Hess's law, and then we'll do a couple of example problems that are a little bit more challenging. All right? So here's an example of a Hess's law problem. It says, calculate heat of reaction, delta H, for the following reaction. So this is the reaction that we want to find delta H for. Okay? And let's just say maybe something is stopping us from measuring this directly. Maybe it's hard to measure directly, or the rate of reaction is difficult, or we just don't have the equipment that we need, or maybe one of the products is going to be dangerous, or we don't have the right setup to do it. So we don't want to do this directly or measure it directly, but we have this known information. So we're trying to find delta H for this reaction given these chemical equations. Okay, now we want to make it so that when we add these two equations together, we end up with this. Okay? And Hess's law says if we can add these two thermochemical equations together to get this one, then we can add these H values together to get this one. Okay, now, in order to add these equations together to get this, we need to make sure that the right things are on the correct sides. The correct things are on the correct sides. So if we look at this, we have NO2 on the left. And in these equations, we only have NO2 one place, right here. Okay, this is where we have NO2. Now in this equation, NO2 is on the right side of the arrow. And we know that it needs to end up on the left side of the arrow. So we are going to reverse this equation. You could call it flipping it, or you could call it reversing it. The other thing we have is N2O4. It's on the right side of the arrow. And we have N2O4, and it's also on the right side of the arrow. So we don't need to flip this equation. We can leave this equation as is. Now, the other thing to think about is how many we have of each. Here we have two NO2s, so if we flip this, we'll have two NO2s on the left. That's good. And here we have one N2O4, and here we have one 2NO4. So we actually don't need to do any multiplying or dividing. If we wanted to, we could multiply a whole equation by 2, or we could multiply a whole equation by 3, or we could divide an equation by 4, okay, whatever we need to do. we can flip them and multiply them as needed so that when we add them together, we end up with exactly this. So I'm going to rewrite this down below. I'm going to write this. So if I reverse this equation, I'm going to have 2NO2 gas, arrow, N2 gas plus 2O2 gas. And then this second equation we're leaving as is. So we have N2O4 gas. We have 2O2 gas and N2 gas. Okay. Now, if I add these two equations together, so I'm just going to put a plus sign here and a line. You see how I keep all the arrows lined up? This can help so that you can keep track of what's on what side. Now, like terms on opposite sides of the arrow are going to cancel out. So I can see that like here I have 2 oxygen gases on the left and here I have 2 oxygen gases on the right. Those are going to cancel out. Here I have I have N2 gas on the left and here I have N2 gas on the right, so that's going to cancel out. And look at all that I'm left with. This comes down here, so we have 2NO2 gas on the left, and here is N2O4 gas on the right. Now take a look at what we have. Compare this equation to this equation. Ding, 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 ding. They're the same. Now, what Hess's law says is if you can add 2 thermochemical equations together to get the equation of interest, then you can add their H values together to get the H for the equation of interest. Okay? But whatever you do to the equation, you have to do to the H. So this reaction as written has a delta H of 67.7 kilojoules. Okay? If you do that reaction in reverse, like we had here, delta H sign gets flipped. So instead of being positive 67.7, it's negative 67.7 kilojoules. And the second equation we just left as is. So this is still 9.7 kilojoules. So whatever we do to the equation, we do to the H sign. So we flipped this first equation. Okay, I rewrote it here. And so I flipped the value to negative. The second one was left the same. If we can add these 2 equations together to get this, now we can add these H's together to get the heat of reaction for the desired equation. So on the calculator here, if I take minus 67.7 and I add 9.7, I get negative 58 kilojoules as my heat of reaction. And there it is. We solve for heat of reaction indirectly using other known equations. This is what Hess's law is all about. Okay? So, summary of the steps I have here. Step 1. Right. Step 1, identify what side of the reaction arrow the different substances are located. Okay? So what's on the left, what's on the right, in terms of what we're trying to find and what we have. You then go around and you flip or reverse equations, okay, so that all of the reactants and products are on the correct side of the arrow, so that when you add them together, you'll end up with what you want. You then need to make sure that you're going to end up with the right number of each type of reactant and product. So you either need to multiply the equations or divide the equations by some factor or quotient in order to get the correct number of reactants or products and in order to cancel things correctly. Once you have reversed equations and multiplied equations as needed. You're going to, step 3, here, sorry about this, you're going to add the equations together and cancel like terms on opposite sides of the arrow. Okay? Now, if those equations add up to the one you're interested in, you then need to do the same thing to the h values. Okay? However you manipulated the equations must be applied to each corresponding heat of reaction value. Okay? So if you reversed an equation, the sign of h gets flipped. Right? If you multiplied an equation by 3, the heat of reaction gets multiplied by 3, and so on. Finally, add the heat of reaction values together to arrive at the heat of reaction for the desired equation. So that's what we did. Now we're going to do 2 more examples, and these are a little bit more complicated because that last one just had 2 equations, and all we did was flip the first equation, right? That's like about as easy as it gets. We flipped the first, and ta-da, that was our answer. Now, our next example problem, you have 3 equations that are known instead of just 2. But the idea is the same. We want to calculate delta H for this reaction, okay? The combustion of propane. So delta H is what we're solving for. This is what's given, okay? Each of these equations is given, and their H values are given. So the first thing we're going to do is look at the stuff that's on the left side in this equation, look at the stuff that's on the right side in this equation, and then find them in here and flip these equations around as we need to make sure that everything's on the correct sides. So the first thing we have here is C3H8. It's on the left side of the arrow. If I look in these equations, the only place that we have C3H8 is right here. And it's on the right side of the arrow. We need it to be on the left side of the arrow. So that means that this equation is going to be reversed. Sorry if that's a little bit hard to read. That's supposed to say reversed, okay, or flipped, because that would put C3H8 onto the left side. Okay. Now, the next thing in here is O2, and if you look at these equations, we have O2 here, and we also have O2 here. If you have something that appears multiple places in multiple equations, leave it till the end. Okay, leave it till the end. Because if this is on the right side, and these things are also on the right side, then the last remaining one will just work out. Okay, so we're going to look at CO2 next. CO2 is also only found in one place in all of these equations, right here. Okay, now CO2 is on the right side, CO2 is on the right side, so that's good. We don't need to flip it. Then we have H2O. It's on the right side, and the only place we have H2O here is on the right side. Okay, so the first thing we had to do is make sure that we flipped our equations so that everything was on the correct sides. We only have to flip the first one. Right? That way that will give us C3H8 on the left side. These are already on the right side, which is good. The next thing we have to do is make sure that we end up with the right number of each of them. We want to end up with a single C3H8. This has a single C3H8, so we're not going to multiply or divide this. We're just going to leave that equation once we flip it. Now, here you can see that you need to end up with 3 CO2s. This is the only place we have CO2, and it's just one of them. So we need to multiply this whole equation times 3 so that we end up with 3 of these. And water is only occurring right here. And we need to end up with 4 of it. So this equation needs to be multiplied by 4. Now, if we do all of this, we're going to have the things that we're interested in on the correct sides of the equations, and we're going to have them in the amount that we want. But there's still a couple of other things, like in here we have H2, and here we have H2, and there's these O2s. But if all of these other things are on the right side and in the right amount, I'm pretty confident that the other stuff is going to cancel out appropriately. But let's check. Let's see. I'm going to rewrite these equations as I have outlined. So the first one I'm going to reverse. So that's going to be, and I'm going to just try to keep all of my arrows lined up fairly well here. It might not be perfect, but let's see. If I flip this, I'm going to have C3H8 is a gas on the left side, and on the right side I'm going to have 3 C's plus 4 H2s, and then I'm going to have a delta H value. And then next, I'm going to have this equation. I'm leaving it as is, but I'm multiplying it by 3. So that means that I'm going to have, on this side, I'm going to have 3 carbons. I'm going to have 3 O2s. And on the right side, I'm going to have 3 CO2s. All right, so I just multiplied the whole equation times 3. And then finally, I have this equation times 4. So I'm now going to have 4 H2s. A half times 4 is 2. So that's 2 O2s. And then on the right side, 4 waters. Now, I'm going to add these together and see what we end up with. Okay? So I'm going to put a little plus sign here. Like terms on opposite sides of the arrow cancel out. Okay? So here we have 3 carbons, and here we have 3 carbons. Those are going to cancel out. Here I have 4 H2s, and here I have 4 H2s. Those are going to cancel out. Now, what I'm left with on the left side is C3H8, so I'm going to write C3H8 as a gas, plus I have 3 O2s, and then also on the left side I have 2 O2s. So if I add 3 oxygens and 2 oxygens, that's 5 oxygens. And then the only thing that's left on this side, I have 3 CO2s, and I have 4 H2Os. Taking a minute, look at what we have left. Look at our equation of interest. Dun-da-da-da, dun-da-da-da. It's the same, right? Same thing. What Hess's law says is, if we can add 3 thermochemical equations together to get an equation of interest, we can add their H values together to get H of the equation of interest. But remember, whatever we do to the equations, we have to do to the H values. So this first one we reversed. So instead of minus 103.8 kilojoules, this one is going to be positive 103.8 kilojoules. I might have to zoom out a little bit. The second equation we multiplied by 3. So if we multiplied the equation by 3, that means we're going to take this number of kilojoules and multiply it by 3. So minus 393.5 times 3 gives us minus 118.5 kilojoules. Okay? And finally, this bottom equation we multiply by 4. So this is getting multiplied by 4. So in summary, this becomes positive, right? This becomes positive. This gets multiplied by 3, and this gets multiplied by 4. So if I take minus 241.8 times 4, I get minus 967.2 kilojoules. Okay. So now that I have done these things to the H signs, if we could add these together to get this, now I can add these together to get this, which is my ultimate goal. So I'm going to add these together. We have this one, which is just still in my calculator, plus minus 1180.5 plus 103.8. And what I get is my final answer, minus 2043.9 kilojoules. And that is our delta H for the reaction of interest. Woo! Kind of seems like a lot, but they're actually really fun. It's like a Sudoku puzzle, but for chemistry nerds, and you're gonna get good at them. So let's do another one because I'm pumped up. This is going to be our last example, and I think it's maybe even more complicated than this one is, just because we were going from the most basic, the simplest, to a little bit more advanced, right? We went from 2 equations to 3 equations, and I know you're thinking, how could this possibly get any more fun? And the answer is, we could do 4 equations, right? And nothing's stopping there from being 5 or 6 either. But this is going to be our next example. So this is the equation of interest. We're solving for delta H. This is known information, all right? So step 1, we need to flip equations so that what we want is on the correct sides of the arrow. So we can start with SO2. If we look at all of these equations, SO2 only appears one place. Not here, not here, not here, not here. There it is. That's the only place SO2 appears. And it's on the right side of the equation. And here it's on the left side of the equation. So we need to flip this equation, or reverse that equation. We know that because we need to end up with SO2 on that side. The other thing we know is, because this is the only place we have SO2, right? It doesn't occur anywhere else, so it's not like SO2 is in a different equation and we're eventually going to add it to this SO2. The only place SO2 exists is here, and we're going to end up with 2 of it. So that means that this equation also has to be multiplied by 2. So we need to flip it and multiply it by 2. That would give us 2 SO2s on the left side, which is what we need. Okay. Next we have P. P also only exists one place by itself in this, and it's right there. Now here it's on the left side of the arrow, and here it's on the left side of the arrow. So that's good. We don't need to flip this equation. But we need to end up with 2 of it, and we only have 1 here. So this equation is going to get multiplied by 2. Here we have chlorine, Cl2. And if we look in these equations, chlorine is here, chlorine is also here. So when we have something that shows up in multiple places, let's just leave that one alone for a little bit and focus on these others. Because if this is on the right side with the right number, and this is on the right side with the right number, and so are these, it's going to make it so that this just works out. Okay? So the next thing is SOCl2. SOCl2, again, only exists in one equation right there. Now, it's on the left side, and it has to be on the right side. But we already established that we're flipping this equation. If we're flipping this equation, that would put it on the right side. And if we're multiplying by 2, that would give us 2 of it. So that's good. We don't need to do anything else with that. Here is POCl3. The only place that we have POCl3 is in this equation. It's already on the right side, and this is on the right side, so that's good. And we need to have 2 of it, so this also needs to be multiplied by 2. Now, the last equation hasn't been involved yet. And another thing that's a little weird is the only thing in this equation that is in this equation is chlorine. Okay? So we know that we need to end up with 5 chlorine. And if we didn't have this equation here, right, if we didn't have this equation here, right now we have chlorine right here, and it's on the left side. If this equation is getting multiplied by 2, 3/2, that's the same as 1.5. If you take 1.5 times 2, that's 3. So right now we have 3 chlorines on the left side. We need to end up with 5 chlorines on the left side. And none of the other equations are going to help. So if we have 3 chlorines on the left, we need to get 2 more chlorines on the left. And if we look at this equation, it has 2 chlorines, but they're on the right. So that means we're going to flip this bottom equation, and that would bring 2 chlorines onto the left side. It would also put 4 HCl's on the right, and that's going to be good because when this equation is multiplied by 2 and flipped, we'll have 4 HCl's on the left, so those will end up canceling out. So I'm going to rewrite these equations as I have outlined in terms of what we're going to do to them. So I'm going to try to keep my arrows lined up. So this one is going to be flipped in times 2. So on the right side, I'm going to have 2, sorry, that's already a little cramped, 2 SOCl2 liquid plus 2 H2O liquid. And here I'm going to have a delta H. On this side, it would be 2 SO2s and 4 HCl. I'm just trying to separate stuff a little bit here. All right, so this is the top equation. All right, I flipped it and I multiplied it by 2. So instead of 2 on the right, there's now 4 on the left. Instead of one of these on the right, there's now 2 on the left. So I flipped it and multiplied it by 2. This next one I'm just leaving as is, but I'm multiplying it by 2. So on the right side, we'd have 2 POCl3. And on the left side, if I take a half times 2, that just gives me a single oxygen. And this times 2 is going to give me 2 PCl3s. Okay, again, I'm timesing this one by 2 as well. So that's going to be, on the right side, 2 PCl3s. And on the left side, 3 halves, that's 1.5 times 2 is 3 Cl's. And I'm going to have 2 P's. This one is just getting flipped. Okay, the last one is just getting flipped. So that means that 2 waters are going to be on the left. Two chlorines are going to be on the left. And on the right, I'm going to have an O2 and 4 HCl. Okay? So this is me rewriting these equations as I outlined. Now, if I add these all together, zoom out a little bit. Let's see what happens if I add these together. All right? So, like terms on opposite sides of the arrow cancel. I have 4 HCl gas on the left, and I have 4 HCl gas on the right. Those cancel. I have an O2 gas on the left, and I have an O2 gas on the right. Those cancel. I have 2 PCl liquids on the left, and I have 2 PCl liquids on the right. Those cancel. I have 2 waters as a liquid on the left, and I have 2 waters as a liquid on the right. Those cancel. And look at what we're left with. I have 2 SO2s. I have 2 P's. And I have, here's 3 chlorines and here's 2 chlorines. So if I add those together, that gives me 5 chlorines. And on the right side of the arrow, I have 2 SOCl2s and 2 POCl3. Look at this equation. Look at this equation. Dun da da da, dun da da da. They're the exact same. If we can add these equations together to get this, then we can add the H values together to get H for this reaction. Okay? Now, I have to change, sorry about the bell. I have to change these values based on what I did. So, if I'm flipping this first equation, this is going to become a negative. And if it's times 2, right? So this is going to become a negative, and it's going to be times 2, so that would be 20.6. So negative 20.6 kilojoules, right? Negative and times 2. This one is just getting times 2. So if we do that, that's 651, let's just put it in here, minus 325.7 times 2, minus 651.4 kilojoules. This equation gets multiplied by 2, so this is just times 2. So if we take minus 306.7 times 2, I get minus 613.4 kilojoules. And then this final equation we just flip, so that means that the sign becomes positive, so that's positive 202.6 kilojoules. Okay. Now, Hess's law says if we can add these equations together to get this one, then we can add these H's together to get delta H for this equation, which is the ultimate goal. So I'm going to add these together. I already have this one put in there. So I'm going to add 202.6. I'm going to add minus 651.4. And I'm going to add minus 20.6. And when I do that, I get minus 1082.8 kilojoules. Going to do a quick double check. On some of these, I'm not sure if minus 306.7 times 2, that's fine. This number gets flipped so that it's positive, that's fine. And this number gets flipped and times 2 negative. Yep, it should be fine. I did it beforehand and I got an answer which was different, but this should be the correct answer. Hopefully I didn't screw that up. I might have put something into the calculator wrong, but I'm just doing a quick double check. Yep, I got the same answer twice there. So unless you are catching something that doesn't look quite right, this should be good to go. I think I plugged everything in. Sorry about that at the end there. Big ideas here with Hess's law, this has been a presentation on Hess's law, is that when you add thermodynamic or thermochemical equations together to get an equation of interest, you can add their H values together to get H for the equation of interest. Hopefully that was helpful. Hopefully you get the idea. Let me know if you have any questions. Thanks for watching. See you back in class.